And do you like to have the mic on? Do you want to?
No, it's fine. I'm going to try to show
Your show.
That's a good practice because I'm
Projecting your voice. Okay, perfect. Up to you. I'm game for whatever. Go for it.
Okay, I'll take So hi everyone, welcome to the first public talk of this year. First of all, my name is Valentina. I'm a master's student here at McGill and I'm in charge of organizing the public talks. If you have feedback or recommendations, then feel free to reach out to me and I'm happy to welcome your suggestions. Also, before we start with the actual public talk, I wanted to briefly say that here at McGill and at the TSI Institute, we are committed to equity, diversity, inclusion. And it's very important for us that everyone feels welcome and comfortable. So if you have any type of concern, please feel free to reach out to me or to any other volunteers, and we're happy to help you. Another thing, okay. So yeah, so let's go back. And so it's my pleasure to introduce Professor Daryl Haggard, who is a professor here at McGill University. Her talk, Into the Deep, Touring a Supermassive Black Hole or Two, is gonna go over the observations by the Event Horizon Telescope of Sagittarius A star. And she will also touch upon Messier 87 and give outlooks about current and future research in the study of supermassive black holes. Please join me in welcoming her here.
I got my fan club here in the front. So I have a pretty loud voice. Can people in the back hear me? Yes. Okay. I am not going to wear. They have these headsets, but they always make me feel like Lieutenant Uhura because they go around the back. So I'm going to skip that. If you stop being able to hear me, you know, just do a Hail Mary, wave at me, and I will speak up or put the headset on. So welcome everyone. Thank you so much for being here. It's really lovely to see so many people out, especially in this very cold weather. So thank you for that. I am indeed going to be presenting work on behalf of the Event Horizon Telescope collaboration. I'm a member of this collaboration, as are some of my team members who are here in the front row. So it's really a privilege to work with this very large group of people. I'll try to feature their contributions throughout as well. The other piece of this work is actually coming from a suite of observatories that are not a part of the Event Horizon Telescope. These are NASA's great observatories, as well as many other observatories on the ground and in space. So I'll try to do my due diligence and shout out all of the fantastic facilities and people that work on this science with me. And I'm going to do that kind of catchy thing that a lot of people do. It's like in vogue for talks now, where you just like give away everything you're going to talk about right at the beginning. And I'm going to do that by showing you two movies. So I promised you a tour of a massive or a supermassive black hole. And I'm in fact going to give you two tours of two black holes, but really more the galaxies in which they reside. And that's partly because my team and I study not only the emission very, very close to the event horizon of the black hole, but the entire context, the entire ecosystem around the black hole. And I want you, please, to do me a favor and ooh and ah while I show you these videos. And the reason I want you to do that is because I'm an observer, I'm an empiricist, I really like data. Theory's cool, I like it as well, but I'm really, truly an observer of the universe. And these two videos I'm going to show you right at the start here, the first of our Milky Way galaxy zooming in on the supermassive black hole Sagittarius A star, it's all observational data. It's really an incredible demonstration of what, you know, human ingenuity, incredible facilities, investment from all of you, from taxpayers, from people the world over to make these observations happen. And I think it's really pretty spectacular as you watch these videos to realize that these are all observations of our universe, of our galaxy, and of the galaxy M87. So we're going to start out kind of sitting here at the position of Earth, and we're going to zoom in and we're going to change wavelengths in order to get a preferential view through all the dust and gas and gunk of the galaxy. And then the second video I'm going to show you is actually going to start at the event horizon at the black hole of M87 and zoom out. And in that case, you're going to see actually this really spectacular jet that M87 has that spans over 7 orders of magnitude, both in wavelength and in space. So get ready. Is everybody ready? Movie 1. Here's your first tour. Okay. Yeah. Thank you. Ooh. That's what you're supposed to do. So at first we're looking in optical and UV light, and you can see there's this dark band across our Milky Way galaxy. That's dust and gas obscuring our view of the stars. But right about here, you'll see a whole bunch of stars start to appear in our line of sight. That's because we've switched to infrared light. Thank you. I love you. And here we have switched again to X-ray light. So X-rays are very high energy photons that manage to penetrate all that gas and dust. You guys are the best audience. I love this already. And then you can just fall asleep after this because the lights are off and the videos are over. So we're zooming way into the middle of the Galactic Center. And in a second, you're going to start to see these stars move. This is actually a time-lapse video for which the Getz group at UCLA won, or actually this might be a Gensel image, but the Gensel and Getz groups won the Nobel Prize 2 years ago for actually monitoring these stars over a very long period of time. And if you look closely, you'll see that there are stars orbiting what appears to be empty space. This was our first tracer of the existence of a supermassive black hole in the Galactic Center. Okay, those lines are not really observations. The stars are observations, the lines are not. And if you were really paying attention, you might have seen a little source flickering right in the middle of the frame. And that's Sagittarius A star, the supermassive black hole that sits at the center of our galaxy. If we zoom in even further with the Event Horizon Telescope, this is the image that we get. When we first put out these images, a lot of people were like, ugh, why are they so fuzzy? And I just want you to know that this is the most high resolution image that's ever been taken ever. Like by an electron microscope, by a quantum computing special microscope. This is the highest resolution image ever taken. It's really like a tiny, 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 tiny fraction of like a human hair between, you know, you all at the back of the room to me. So it's a very high resolution image. And it's showing us the hot emission, the hot gas around the supermassive black hole at the center of our very own Milky Way galaxy. So there you go. There's tour number 1. Now we're going to leave our galaxy behind and we're going to move into the Virgo cluster. So the Virgo cluster is a cluster of galaxies that resides fairly close to the Milky Way. It's the closest cluster of galaxies. It's a sort of a modestly rich cluster of galaxies. And right at the heart of that galaxy cluster is a galaxy called M87. It's known as the brightest cluster galaxy. And in that galaxy is another supermassive black hole that we call M87 star. We use that little star symbol. So this is Sagittarius A star. Sorry, these names are a little bit ridiculous. The reason this is called Sagittarius A star is if you look in the direction of the constellation Sagittarius, you are actually looking toward the center of our Milky Way galaxy. A means, the capital A means it's the brightest radio wavelength source in that direction. And the star means it's in a galactic nucleus. It's in the center of a galaxy. So M87 star is the galactic nucleus of the galaxy M87. Okay, so here we go. Here's another tour. Our next, okay, all right, that's enough. So this is starting now with the M87 image. And we're going to zoom out in this video over, as I mentioned earlier, 7 orders of magnitude in length scale. So, and as well as over 7 orders of magnitude in wavelength. And the thing that you'll see immediately here is that we don't have that kind of fidelity, that kind of resolution to image all the stars and gas and dust in the M87 galaxy. It's much further away than Sagittarius A star. But this supermassive black hole drives a very spectacular jet. And as we're taking a step out, we've moved from a fraction of a light year to 1,000 light years, and then out to 10,000 light years and to 100,000 light years. This jetted structure is persistent across all of these size scales and all of these wavelengths. And so when we use multiple different observatories and wavelengths of light, we can actually trace out these very interesting energetic structures. It is in fact an open question in astrophysics how a supermassive black hole, something that is fairly small in size, very heavy in mass, but small in size, could actually drive a jet over these many, many orders of magnitude in space. We think these jets can potentially interact with all the material in the galaxy and change the conditions under which the galaxy evolves in time. And we know for certain that these jets actually can puff up huge bubbles in that intercluster medium in between the galaxies and the galaxy cluster and create these very interesting substructures on extremely large scales astrophysically. And so we call this, when you have a jet coming from a black hole interacting with its environment, we call that feedback. And that feedback, we think, is really key to understanding how galaxies evolve across cosmic time. All right, so that was the spoiler. You've seen the tours. If you have other things to do, you can call it a day. You can pull out your social media, whatever you got to do. But now I'm going to actually talk a little bit more about these collaborations and how these images, in particular, the horizon scale images, are made and what we think we're learning from some of these different observations. So as I mentioned at the outset, I work as a member of the Event Horizon Telescope collaboration. And this is a rather unusual kind of telescope. So you'll see here a picture, and in fact, there are several other observatories that have joined this array. This is a worldwide array. So these observatories are actually spread across the globe. They are individual observatories in their own right. So you'll notice each one of them has its own name: the Large Millimeter Telescope, the Caltech Submillimeter Observatory, the South Pole Telescope, etc. Each one of these observatories operates and does science of its own making, serving the community in a general way over the course of a year. But once a year, for roughly around 10 days, people like Nicole here in the front and I get all these telescopes to work together in concert as a single array. And that's quite a feat. It's actually very hard to do. It's really difficult to convince the globe to have good weather in all sites, all on the same night at the same time. Really tough. In fact, we're often closed down because it's snowing somewhere, or the winds are high somewhere, or humidity is just too high, or whatever. Winds for radio observatories are particularly pernicious, as is snow. So this is a challenge. We do a lot of kind of real-time decision-making about whether or not we're going to observe on a given night or not. So you also have scientists spread across the globe trying to figure out whether or not they're going to be operating those observatories on a given night for a particular target. So this is the Event Horizon Telescope Array. The way this works is a technique called interferometry. Many of the people in the audience are in fact radio astronomers and interferometrists of their own right. But for those of you who have never seen this kind of thing before, what happens in an interferometer is that you're actually clocking the arrival of these wavelengths, these wave fronts of light. So you can see this depicted here as these sort of squiggly lines
This is light coming, say, for example, from a supermassive black hole like Sagittarius A star. At the individual observatories, you actually clock the arrival of these wave fronts, these peaks and troughs, and then you correlate them and you figure out what the delay is across these two. And that allows you then, because you know how far apart your two observatories are, that allows you to recreate an image as if you were measuring these two photons at the same time from the same source. And so this correlation technique allows you to operate these two very distinct observatories as if they were a single dish. Of course, that dish doesn't cover the entire globe. That dish only covers a small patch here and a small patch here. So it's sort of like if you have a mirror that's mostly black and has a couple of little reflective spots on it. Those are almost like your observatory dishes. So you can only really collect photons and tiny little patches around the globe, which is part of the reason that our images are imperfect and we have to make some inferences about what's actually happening in the data. So this is a very tricky data analysis method, and in particular for the Event Horizon Telescope, because it's using very disparate different dishes from all over the world, this data analysis challenge is a big part of the work that the scientists in this collaboration do. So here's a little picture showing you once again just sort of how cool these different observatories are, and getting at one of these fundamental things about interferometry. So each one of these lines we astronomers would call a baseline. So if you imagine you all in the audience are Sagittarius A star, you're the supermassive black hole that I want to observe. Combinations of observatories, of two different observatories that are connected by these lines, can actually only look in your direction for a short time as the globe rotates, right? So those lines that I was showing you, or that the movie was showing you, I'll show it one more time, as the whole Earth rotates, those lines have different visibility toward your direction. And that also changes a little bit exactly how much resolution we have in our images. The length of this baseline has a major impact on how precise, how sensitive our array is, how precise we can do our resolving in that image. And so this is called long baseline interferometry. And you'll notice that we're actually using the rotation of the Earth to give us each one of these different lengths of baseline over the course of the night. So that's a big computing challenge. You have to compute these correlations between the arrival times for your signals across lots of different baselines as the globe rotates. And so the other big part of the Event Horizon Telescope, so there's the telescopes, there's the correlators. These are the computers, one set of correlators that does a lot of this heavy lifting for us. One thing that always kind of shocks and appalls me, as I told you, I'm an empiricist, I love data, but it turns out like our disks actually contain so much data that after we've correlated it, we actually throw out a lot of the raw data. That's just tossed in the trash. That's it. You can never recover it. So you have to do it right the first time. Otherwise, you're losing the science that you were trying to do. The other thing that the EHT is a whole lot of people. So I mentioned this already. This is one snapshot from a group of us at a meeting in Granada, Spain a few years ago. So it's not just an Earth-sized telescope, it's an Earth-sized collaboration. There are at least 250, maybe closer to 300 scientists now from all over the globe that work on this collaboration. We need operators at all of those different observatory sites. We need simulators, scientists of every different stripe to be able to do this kind of work. And so it's very cool to work in a big international collaboration like this and make all this science possible. I'm somewhere in this image. I had just gotten in because my flight was delayed, so I look like I'm half asleep, but that's the way it goes. And so the upshot is that the Event Horizon Telescope can now create these really beautiful, really truly spectacular horizon scale images. So I'm going to walk you through a little bit how we understand these two supermassive black holes. I'll do a sort of a side-by-side comparison of them, showing you some of the features that are similar and some of the features that are different between the two black holes. This particular image is of an M87, that second black hole I showed you. And I will just tell you that some of the bright and dark patches that we see for M87, we actually think are real in the sense that these are showing us something interesting about the accretion, about the material flowing onto the black hole. So just to take one of those features, and I'll talk a little bit more, but you see how it's brighter down here on the bottom. Part of that is because we think the sense of rotation for the material in the black hole is actually rotating toward you on the bottom and away from you on the top. And so you get a little bit of Doppler boosting, a little bit of movement boosting, a little more intensity because of that in the bottom than you do in the top of the image. So that's just one of many different sort of physical effects that is imprinted onto these images that we try to extract out to understand the physics of very strong gravity, very intense gravitational fields in the region very, very close to the event horizon of this black hole. Okay, so this particular one, as I mentioned already, is M87 star. It also has a beautiful native Hawaiian name, Hawaii, which means something like the unfathomable darkness, which is actually pretty cool. It's from a creation poem in indigenous Hawaiian sort of history. And this is, as I already mentioned, in the Virgo cluster. The other black hole that we've managed to image is Sagittarius A star, the one in the Milky Way galaxy here. So this is our own supermassive black hole. So you'll notice right away, if I just go back and forth between these two images, that they look kind of similar. I had a lady in a donut store once ask me why the black hole looked like a sunset. And I was like, no, why are we talking about this at a donut shop? But the color scale here is, it sounds bad to say that it's artificial, but in many ways it is. In fact, you know, when you get 250 scientists together, they can actually debate for days and weeks about whether it should be purple or orange or green or what. And indeed we did. This kind of orange color scale was picked out as one that sort of shows the contrast in the image the most effectively. And then there was yet a different debate about whether or not we should have Sagittarius A star and M87 star be the same color or two different colors, so people could tell they were two different black holes. So like I said, a bunch of scientists together can come up with all sorts of things to argue about. But we decided to keep the color scale the same. It's a so-called false color image in the sense that these are millimeter wave photons that we're seeing. Our eyes cannot see those. And so we have to adapt that intensity map into something that we can actually visualize with our eyes. Okay, so here we come, the side-by-side comparison. So many of you probably have seen this XKCD comic, which is a fantastic sort of sense of sort of physical scale for this supermassive black hole. So this is M87 star. It has around 6.5 billion times the mass of our own sun. Astronomers use a lot of relative units. This is very helpful for us because if I were to tell you how many grams this was, it really wouldn't be very meaningful. Already 6.5 billion is a lot of solar masses. And that amount of mass, right, 6.5 billion times the mass of our own sun, fits into something that is actually not very much bigger than our solar system. This white circle here is showing you the orbit of Pluto. And this other little dot here is showing you Voyager 1, which is the spacecraft that humans have sent the furthest away from our own planet of any other object, right? So in our entire existence as humans, trying to explore the cosmos, the furthest we've managed to get in terms of spatial scales is something like the event horizon of this supermassive black hole. So that's a lot of mass in a very small amount of volume, in a very small amount of space. So in contrast, just to put this in context, our Earth is something like 3 millionths of the mass of the sun. So this is the globe that we sit on that we think is very impressive, that we think is very massive and large, is actually really super duper duper tiny compared to the amount of mass that is packed down into this supermassive black hole. But our Earth, if we really wanted to, could become a black hole itself. All that matters is how much mass you've shoved into a small enough volume that you can trap light in there. And so if you could make our Earth into something the size of a sugar cube, you could make our Earth into a black hole. So if you could take, your mom, the ocean, a mountain, any of the relatives you're sick of after the holidays, and smush all of it down into something the size of a sugar cube, our Earth too could be a black hole. What that means is just that the escape velocity, the velocity that an object has to achieve to escape off the surface of that object, of this world, of this sugar cube in this case, is faster than the speed of light. So even light can't get out. Light is trapped, and that is one of our sort of descriptive descriptions of what a black hole is. Okay. So now side by side, here are these two black holes we've imaged. It's very easy to imagine, because I've showed you these two images side by side kind of at the same size scale on the projector, that they themselves are the same size, but they are not. So here's that same kind of XKCD visualization. Here's Pluto's orbit. This is M87 star. And the entirety of this supermassive black hole Sagittarius A star would fit way down deep inside here too. So it's actually much, much physically smaller in terms of spatial scale than M87 star. And it's also less massive. And so here now, drawn in a white line, is something roughly the size scale of Mercury's orbit. So these two black holes are different in some ways, similar in others, but certainly they are different in size, in physical size. So M87 star has around 6.5 billion times the mass of the sun, as I already pointed out. Sagittarius A star has 4 million times the mass of the sun, so about 1,000 times less mass. And correspondingly, it is considerably physically smaller in terms of spatial scales. I think we have, yeah, okay, here's a nice little way of visualizing this. So Sagittarius A star here in our Milky Way galaxy is around 27,000 light years away. M87 star is much further away, but we're using the power of, a computer to drag it toward us and try to put these two on the same scale. So we basically pulled M87 star to be the same distance away from us as Sagittarius A star, and you can see that it is a much, much, much larger object. And the reason we see them as the same rough size on the sky is just a projection effect, right? The one object is much larger than the other, but it is much further away. And so it looks like they're roughly around the same size, even though they are, in fact, not. Okay, so these are these two beautiful black holes. One thing that is already obvious here is that the ring size, if we were just kind of to draw a line around the size scale of the shadow, we're measuring this here in micro arc seconds. And you can see that the sort of size scale of this ring for M87 is around 40 micro arc seconds. It's actually slightly larger for Sagittarius A star. So this is the reason that we're imaging these two black holes with the Event Horizon Telescope. It's because they are massive enough and close enough that we can actually hope to resolve this sort of bright ring with a dark shadow in the middle. I'm going to give you a kind of a hand-waving description, and then I'll show you in a minute a different simulation to help make this a little bit clearer. But one way that it's nice to think about these images is to think of, and this is, with the LA fires, probably you've seen many images like this. If you imagine that I am a person standing here and there is a very bright thing behind me, maybe a fire or a bright screen, I am going to be a dark silhouette in front of that bright thing. That is more or less what you're seeing here is the dark silhouette of the black hole projected against something bright that is sort of all around it. It also has a gravitational bending effect. So the thing that is slightly different about a black hole is because it influences gravity. If I were a black hole, I would not just be blocking photons behind me, the light coming from behind me. I'm also kind of taking it and pulling it in your line of sight using gravity. So gravity actually redirects those photons all around me into your line of sight. So that black hole shadow is enhanced even because it's basically redirecting photons into your line of sight using gravity. So probably you've heard a little bit about Einstein's theory of relativity, and one of the consequences of it is that gravity influences light, and light will travel along the easiest path it can in a curved space-time. Okay, so I was talking about some of the things that are similar and some of the things that are different between these black holes. Another thing that is very different because their masses are different is the timescales on which they change. So believe it or not, this movie is actually changing. This is a GRMHD, a general relativistic magnetohydrodynamic movie. You don't have to worry about that whole long acronym, but it's basically a simulation of what we think is happening in the accretion flow. When we image this with a telescope, it's blurred out, so you can't see all of this nice sort of fine detail in our EHT images. But in a simulation, you can see that. And you'll notice that the more massive black hole, M87, is varying on timescales. I'll go back and then go forward again just so you can watch this, is varying on timescales that are much longer than Sagittarius A star. So once again, remember these two differ from each other by a factor of about 1,000 in mass. And we believe that their timescales for variability are also different by about that factor. So we see variability in Sagittarius A star over short timescales, minutes to hours. For M87 star, we see variability on timescales more like weeks to months, even over years. And so this is a very cool thing that we can try to study as we observe these two black holes over time. I will, though, tell you that this very rapid variability over hours is actually a huge challenge for making images of Sagittarius A star. So think back to the beginning of this talk where I was showing you how the Event Horizon Telescope works, those baselines between the different telescopes and the Earth turning. Does everybody remember that? Okay, so I'm trying to make an image and I'm trying to patch together like little bits of my mirror as my Earth turns so that I can make a really nice high resolution image. If my source, if you guys are jumping up and down and varying around while I'm trying to take that picture, it really confuses my image synthesis, my ability to make a very precise image. If you're varying while I'm trying to take a picture of you, it's sort of like sports photography or something, right? If your athlete is like zooming around while you're trying to take a picture, your picture is going to end up blurred out and be harder to interpret. So we have had that challenge with Sagittarius A star. It varies while we are trying to image it over the course of hours as the Earth turns. And that has made the analysis for Sagittarius A star both very, very interesting, but also very hard. And so if you look at the dates here when we publish these things, you'll notice that these publications are 3 years apart. That is partly just due to the challenge of trying to take into account this intrinsic variation in the black hole. Now I'm showing you two images of M87. These are both M87 star, not Sagittarius A star and M87 star, but these are separated by a year. This is April 2017, and this is April 2018. So these are observations taken 1 year apart, roughly. And you can see these bright structures at the bottom of the image have changed over the course of that year. So this is now showing us that same variability, but over longer timescales, over year-long timescales, which is exactly what we would expect for this more massive, supermassive black hole. And so we are starting to build up enough information about these horizon scale images that we can start to make the world's crappiest movies. Right? This is not really like, you know, even Charlie Chaplin era yet, right? So we're getting there. We're working really hard. And I will say that one of the big goals of our collaboration over the coming years is to start to actually launch movie campaigns that take time-lapse images and allow us to actually start to try to see how the material is responding to, say, the rotation of the black hole, to changes in how much material is flowing onto the black hole, etc. So this is a very exciting thing that we're just at the tip of the iceberg of trying to figure out how these variations happen. We're really excited about it, though we do recognize that from the perspective of the public, this might be a little underwhelming as a movie. Another thing that we're really excited about, and this is a huge trend in astrophysics right now, is trying to understand the magnetic fields in the vicinities of these black holes. This is always the astronomer's dream, is to try to understand the magneto part of those magnetohydrodynamic simulations. And you can see here, these are polarization vectors, not exactly magnetic field vectors, but they do correspond to the magnetic field strength. And you can see these beautiful field lines that seem to sort of wrap around the black hole, probably because the magnetic field is pinned to the material as the black hole rotates and causes this very interesting magnetic structure, which may very well give rise to those incredible jets that I showed you in that very first image of M87 star. So another fascinating topic that we're all working very hard to understand better. Okay, so this is another promised movie. This is a slightly more precise version of Daryl standing here telling you, oh, and then I have light behind me and I pull it in the direction of your view. You can see here now, if you imagine that you all are standing or sitting in this image plane, that when the photons come and interact with the black hole, this is sort of the image of its distortion of space-time, you can see those photons get redirected around the black hole. And that this little number ticker is showing you something, a proxy for how many times the photon interacts with the black hole. And you can see that for photons that have stronger interactions or more sort of perturbations as they come in, that they actually get focused into a tighter and tighter ring that traces out the sort of gravitational properties of this black hole. So now you're seeing all those different, the first, second, and third order photons all mixed together. And you can see there's this bright ring here, which is the product of the multiple interactions, and all of these slightly less focused photons that build up that wider kind of larger scale image around the black hole. And so this is actually the structure within these Event Horizon Telescope images is actually a very powerful probe of how photons interact with black holes in this very unusual, very strong gravity environment. And another future goal of a lot of our projects is to actually be able to resolve this so-called photon ring. So this very, very, very uniform ring that you're seeing in this simulated image comes from those multiple photon interactions with a black hole. There's a very cool project called the Black Hole Explorer, BEX, which was just recently funded. It's led out of the Harvard-Smithsonian Center for Astrophysics. And its objective is to actually put an observatory in space to talk to all of these observatories down on the ground so that we get an even longer baseline, right? We're currently kind of stuck on our globe. We can't get baselines that are any bigger than the diameter of the Earth. But if you put something into orbit, now you can actually get even further away, make a longer baseline and get higher resolution. And so the BEX mission is a very cool, very exciting new thing that was just funded like last week or something. So this is just now a still image showing you the kind of combination of photons that are, singly perturbed by the black hole, multiply perturbed, and then many multiply perturbed by the black hole. And they build up to give you the images that we see. Okay, right. So I talked to you a little bit about Sagittarius A star and how it's difficult to image. This is Sagittarius A star's image. You'll see it's got three kind of bright spots. I told you a story about M87 and the material flowing toward you and that making it brighter at the bottom. I'm not going to tell you that story for Sag A star. It turns out that these bright spots we don't trust yet. So we have created this synthetic image. I'm going to show you a little about what goes into the sausage for doing that. But we're not completely confident that these bright spots track to something physical in this image yet. I can give you one example of why we're not confident. It turns out that along this axis of the image, we actually have some of our best observatories. And so we might just be more sensitive along this particular axis, which just means that we're pulling more photons in certain parts of this image than in others. And that just makes it look brighter here, but we're not really sure it's real. So in this particular case of Sagittarius A star, partly because of its variability, we need to build up a larger suite of observations in order to really understand which of these are persistent bright spots and which ones of them are just sort of artifacts in our imaging. Okay, so I told you that Sagittarius A star is challenging because it varies. I also told you that the way interferometry works is almost like you've got, a classical telescope mirror, but you can actually only collect photons in funny little patches. What that means is that when we make these images and share them with you, they're in fact reconstructions of us trying to fill in all the information that we don't have. So if you have limited information, maybe only 4 notes in a scale, and you want to try to put together all of the rest of it, you can fill in those gaps in a lot of different ways. And so we do that through simulation. We build up a whole bunch of simulated images, and then we compare them to the image data that we have from our observatories, and we try to figure out which things are closest to truth. And so this is now a sort of a slightly dizzying film of all the different image reconstructions you can make that are truthful to the data that we collected for Sagittarius A star. You'll see there's a lot of images. So we used machine learning, which is really good at image recognition and image classification, to combine these all together and classify them into different categories of image types. And so you're going to see in just a second, this image is going to kind of deconstruct into the 4 different classes of image that we think might characterize the black hole. So this is image classification now done by machine learning. There's the green class, the blue class, the pink class, and the yellow class. That's not what we called them, but there you go. And you can see that these are 4 different image types, all of which are truthful to our data, but that look fairly different to our eye. Because we're all a little skeptical of machine learning, I will say we also made humans classify all of these images as well. That's one of the other things you get to do when you're a member of a 200-person collaboration is click through images and classify them, which is actually dead boring, but we did it anyway. And we came up with very similar classifications to kind of just proof positive the machine learning algorithms findings. So you can see here, this is part of the reason I told you don't overly trust those spots in the image, because I can make a truthful image that doesn't have much of a ring, just kind of has two bright spots, one where there's a bright spot here, one but there's no bright spot here, etc. So there's still too many gaps in our knowledge for us to feel completely confident that one image is exactly truth. But we do actually have a pretty good way of weighting these different image classes and coming up with a kind of a synthetic image that we think is our best approximation right now. And so these are those same 4 image classes. We basically took the number of things that appeared in this grouping, which you can see is a small yellow part of this histogram, the number here, the number here, the number here. You can see this was the most common image reconstruction classification. And then we weighted them according to how often they occurred, combined them together and made this overall image that we shared with the public. So I'm showing you this just to say that there's a lot we don't know still, and we're doing our best and trying to get you these really cool images and to analyze them ourselves, but there's still quite a bit of wiggle room, and these could change a bit as we get new data over the coming years. The other thing we can do is compare these not to synthetic images, but to simulated images, which are similar to the ones I showed you before. And then we can rule out certain classes of simulations. So for example, if the simulation does not reconstruct the size or the shape or the spectral slope, the sort of different amount of photons at different wavelengths of light, we can actually rule out some of the GR-MHD models until we have a suite of models that we think are most truthful to the data that we have collected. And so this is another way that we can try to back physics out of studying these images and studying their variability, studying their different kind of conditions and other wavelengths, et cetera. And so we do a lot of building up of libraries and catalogs and comparing one thing to another in order to try to really understand the data that we've collected and also understand the physics we can take away from it. All right, I'm in my last couple of minutes here. I will say that, as I mentioned at the beginning, we don't only look with the Event Horizon Telescope, we also look with a whole other array called the Global Millimeter VLBI Array, the East Asian VLBI Network, the Very Large Telescope, which observes at infrared wavelengths, and then also we use observatories from space. And we do this to look at the environment and the larger structures around the black holes at the same time that the Event Horizon Telescope is imaging them. And this gives us the broader context, the sort of ecosystem, as I said before, for these black holes. That was the suite of telescopes we had for Sagittarius A star. With M87, we have an even larger suite of observatories that all observe alongside the Event Horizon Telescope. So you can imagine now, as people that have worked with me on these papers know, that you go from having a few hundred authors, which is already an enormous pain, to having like 700 or 800 authors on a single manuscript. And let me tell you how many people can find a lot of typos. And tell you about the same typos 750 times. So it's really a heavy lift to work with this large number of people, but they are all brilliant and extremely hardworking, and that really gives us some fantastic science. So why do we do this? Why do we care? I've been talking a lot about these horizon scale. This is all now just artist impressions. This is the EHT image in an artist kind of way here. So this is M87. And you can see again, this sort of little notional size of the solar system in there. But I've also showed you that beautiful video, kind of illustrating this jet that we think is emanating from the vicinity near the black hole. We think there's actually hot gas that extends way away from the center part of the black hole out to fairly large distances away from there, as well as over those very, very large number of size scales and energies. And we'd like to understand how we can connect up our GR-MHD simulations to the images of the black hole and how this black hole might be connected to this really impressive jet that we see launched from M87, which might help us constrain models that help us figure out how black holes and galaxies are interacting as they grow over cosmic time, how that spreads photons and other kinds of things into the universe for us then to observe as astronomers. And so this is that picture that I showed you the video of, but now just as a still for M87. This is the Event Horizon Telescope image, and this is all what we get from combining it with those other observatories I pointed out, the Global Millimeter Array, the VLBA, et cetera. These are all those different arrays that look alongside us, as well as telescopes in space. This is from Hubble, Swift. This is also Swift, the Chandra X-ray Observatory, NuSTAR, and Fermi. So they all show us different parts of these structures. You can see certain kinds of things like this knot here. Here's this knot gets picked out in the X-ray and in the optical UV. We see these little structures that we're still trying to understand. Are there really gaps here, or is that just our observations? So we're working very hard to link together these different wavelengths and size scales to understand how this jet is launched and how it carries so much energy persistently over a long time, over so many different, such a large range of size scales. So M87 has a very interesting ecosystem, in particular this jet. Sagittarius A star itself is very different. So you can kind of ignore these two top images. They're X-ray images. But down here in the bottom panels, do you guys remember in that very first video I showed you those stars that were orbiting around Sag A star? Okay, so now this is an artist's impression of those stars. And this kind of hot fuzz around here is actually material that comes off of those stars as winds. The stars are massive stars and they push mass off of their surfaces. We call those winds. And they build up this sort of reservoir of gas, very tenuous, hot gas. And that is the gas that is actually available to then accrete down onto, to fall onto the black hole. So this whole thing is interacting, and there's this beautiful simulation. We'll see if YouTube will let me play it for you. So this is now a simulation of what those stellar winds look like in the vicinity of the black hole. This is always very touchy. Okay, so we're zooming into the galactic center here, and you can see these very, very bright stars. Some of them have little disks around them. And this hot material, this is all hot X-ray emitting material, is being blown off of the stars and is then available to accrete onto the supermassive black hole, which you can't really see in this image because it's very faint compared to these hot, tenuous stellar structures. Am I able to go kind of halfway through, you'll see there's a little accretion event onto Sagittarius A star, and it basically blows out a whole bunch. So I think it's coming up in just a second. The whole color scale will change. Wait for it. Wait for it. Oh, now it's rewinding. I must have gone ahead too far. Okay, now you just get to feel again nauseated. Okay, so basically you're accreting material into the black hole, and then it undergoes right there an outburst and blows a ton of this gas away from the black hole. And then the gas has to build up again from the stars so that it can accrete back onto the black hole. So we think this kind of interaction is one of the reasons there's all this interesting variability in the vicinity of the black hole. So really, really interesting dynamical interactions between the black hole and the environment around it. Last thing I'll say before I wrap up from tonight's talk, and just, get excited about black holes in a more generic way, is that we've just collected and announced. Nicole and Zach can tell me, this is a shout out to two of my grad students sitting up here in the front. Nicole and Zach are part of this paper. It was published last week. Our very first observations of Sagittarius A star, which is one of these two black holes, with this brand new observatory called the James Webb Space Telescope. And so we observed the Galactic Center here in our Milky Way with the James Webb Space Telescope using a mid-infrared instrument and detected the black hole for the very first time. And we detected it during one of those I showed you in the previous video, that kind of bright outbursty event. We think Sagittarius A star actually has these kind of flaring outbursty events with some regularity. And that's what you're seeing mapped out here in these James Webb observations. You basically can't see anything, can't see anything, can't see anything. And then this flare kind of goes into outbursts, and you start, the black hole goes into outbursts, and you see this beautiful flaring event, which could really only be picked up by this really fabulous new space observatory, which is detecting the black hole for the very first time at mid-infrared wavelengths. So very exciting. We were really thrilled to have this result, and we'll hopefully have some more from James Webb soon. Okay, so here's the Daryl gets excited. I just want you all to walk away feeling like black holes are the bomb. And so, I'm going to use Nobel laureates to say that, black holes have really just been in the zeitgeist recently. In 2017, there was a Nobel Prize in physics to the first gravitational wave detection, which was a signature in the kind of ripples in the fabric of space-time from two black holes merging together. So this was a fantastic discovery by the LIGO Virgo collaboration. And these are the three recipients of the Nobel Prize for that one. Near and dear to my heart, and this talk was the Nobel Prize in 2020 given to Roger Penrose, Reinhard Genzel, and Andrea Ghez. And these two in particular have done this tracing of stellar orbits in the Galactic Center, which you're seeing in the movie here, which was the first measurement of the mass of the black hole. Basically, you're seeing little Keplerian orbits, these stars orbiting around more or less empty space. The white star is just there to guide your eye. And that gave us a really precise mass for the black hole in our own galactic center. And then somewhat to my consternation, just this year, yet another Nobel Prize went out. This was actually to AI, to John Hopfield and Geoffrey Hinton. So machine learning is really, really cool. Is it physics? I think so. But the thing that was extra funny and got everyone in the Event Horizon Telescope collaboration all in a Twitter was that they showed the black hole image during their Nobel laureate talk, and everyone was like, why did they put M87 upside down? As if the black hole cared whether you put the bright spot upside down or right side up. But boy, this was like really distressing to the Event Horizon. So anyway, so even when the Nobel Prize goes to AI scientists, we're very excited to see our black hole images here in the mix. And so I will leave it there and happily take questions from anyone.
Sure. Talk. As you said, we have 30 minutes for questions. Yeah, so why did you choose to observe M87 first?
So it turns out that we actually observe M87 and Sagittarius A star during the same week. As I said, we have to be very fussy about weather, and the weather has to be good in lots of places. And on the globe, certain objects in the sky kind of rise and set at different times. So there's some nights where you're more likely to get a good observation of Sagittarius A star, other nights where you're more likely to get a good observation of M87, and then you have to factor in weather and, some electronics went down at this observatory or that observatory. And so there's a lot of these very logistical things, but the campaigns that we run for the Event Horizon Telescope collaboration are typically around 10 days to 2 weeks long. We observe all of our targets. This includes M87 Sag A star and then a suite of other objects that are interesting. We can't get their event horizons, but we can see beautiful jets. We can do all sorts of other cool science. And so we always observe them at the same time, but are in the same week or week and a half. But we published the M87 images first because they're not as hard, because that variability thing made the Sag A star images a lot harder for us to manage in a data sense and an interpretation sense. And so they got published a couple of years later. But the other part of your question is why those two black holes? And it turns out those are the only two black holes whose event horizons are large enough in projection on the sky for us to actually see the black hole in projection, that black hole shadow or black hole silhouette. So maybe if we can get Bex up into space and we can do, some refinement, add some additional, sensitivity by adding more telescopes on Earth, there might be a couple of other black holes where we might get down to that event horizon, but really those are the only two that are the combination of bright enough and large enough in projection that we can take their snapshots or their images. I'm going to let you choose the questioners.
Get my question in early because I am totally ignorant of this, and so I'm speaking as a complete outsider, trying to make sense of this really for the first time, although I did actually read a little book on black holes. But anyway, what we're looking at when we see these donuts are photons, which is like lensing, right? Basically, it's like lensing, because we can't see the black hole itself. So you're asking us to believe, you and the hundreds of people who are doing this, want us to believe that we can get information about the black hole from the distortions, the bending, because of the gravity, right? The bending of the beams of light coming from elsewhere. Let me try and say it another way. When I see at the very end the pictures of celestial objects circling or influenced by the gravity of the black hole at the end, I can see, yes, very clearly, I can see here how it makes sense that these moving objects which you can see make sense of something which by definition we can't see. But for a simple-minded person, and I'm sure I'm not the only one who would see this for the first time, it's just so hard to believe that anything interesting can be gathered. This is what the main purpose of your talk, I think. So hard to believe that anything substantial could be drawn from these distorted beams of light which are showing up as donuts.
Okay, I'm not sure that I have a question, but I think that you want to know what physics are we learning by seeing, or what physical properties of the black hole are we learning by making these images that maybe we didn't already know from some other means. So the things I can tell you are these. Those beautiful dynamical measurements that you're pointing out, where we're seeing stars observing around empty space, gave us our first hint, or first more than hint, good measurement of the mass of, say, the black hole Sagittarius A star in the Galactic Center. From that mass, I can then use general relativity to make a prediction for how large that shadow should be. But I can't validate that prediction if I don't ever take the image. So the first thing the images gave us was a validation of the prediction for how large the event horizon should be if I have the mass measured from those other dynamical measurements. So that may not sound impressive to you, but now I have a tool. There's only one black hole I can measure stars going around it. That has to be really close. That has to be in my own galaxy. By the time I get out to M87, I can't measure stars going around the black hole. They're too faint. It's too far away. So I've used Sagittarius A star as an important test of the principle that the black hole mass that I've measured dynamically matches the one that I've measured in the image. Now I can use that to extrapolate that test to M87 and say, yep, I've taken an image, I see the size of that image, and from that I can infer a mass. So I've now got kind of a tool, like a ruler that I can now use to actually infer black hole masses. Black hole masses are notoriously difficult to measure because all of our measurements have to be so indirect because we don't have emission coming from the black hole itself. Okay, so that's a very simple first step that we made. The other thing that we can do is we can use the predictions of general relativity to get a sense for things like that variability timescale. So now if I can do multiple measurements of these black holes, I can compare them to GR. There's actually quite a few different predictions GR makes about magnetic fields, about how much lensing we should measure, those structures like that photon ring. So all of these become actually slowly over time very precise tests of whether or not general relativity really describes the universe in this very intensely strong gravitational regime. It's the only way we can test that. We cannot build a lab here on the Earth that creates strong gravity. We can do weak gravitational experiments, but we can only really do these tests of GR in an astrophysical setting. And so then we bring in things that are a little more complicated that you might be more skeptical of, like those GR MHD simulations. We compare those to our observations. We look for concordance between the theory and the observations, and then we improve the observations, we improve the models, we try to improve the concordance, and we try to learn something about you know, our theories and whether they're really describing the universe. So, you know, I don't know if that's satisfying to you as an example, but certainly having more than one test of the same, or more than one way of measuring the same property is the only way we can validate our theories in order to then try to apply them more generally. So I think these black hole images are a really important step in kind of convincing ourselves that the light and then the mass, you know, in the form of stars are telling us the same story.
Thank you, Brad.
Yeah, for sure. I'm going to go all the way to the back in the yellow hat because your hand was up early. Mhm.
Why there's so many possibilities? What's the outcome when data
Yeah, so the best way I can say that is that the data that we collected is imperfect. It doesn't tell us exactly what every part of that image should look like. It gives us sort of a patchy view of the image. And so that means that I could fill in the parts that I'm missing a lot of different ways. And so then I can simulate all those different ways that still match the parts that I do know, but I can fill in the gaps in all sorts of different ways. And so I do that in the most intelligent way I can. And that then gives me all this whole big catalog of different possible images. So I showed you that the picture of the globe a few times that has those red lines between the different telescopes. If I could completely plaster the Earth with telescopes so that there was no room for you or me anymore, just telescopes, then I could get a much more complete number of baselines, little short ones, long ones. I could get much better sensitivity across all parts of that image, and I would have fewer gaps, and I would have a more trustworthy image, and it would then limit the number of different possibilities for filling in little holes. But right now, we basically have a very patchy view that leaves a lot of room for possibility between those different things. And that's how we basically try to capture all that uncertainty and make these big libraries of images, and then we classify those different images to try to give us some intuition for what the most likely right answer is. And then future observations will help us also fill that in.
We have one question from our online audience. So the light ring is not a picture of an accretion disk, but of light flowing around the black hole. Does it mean that there is no accretion disk around this supermassive black hole?
So there's material around the black holes. So the photons are coming from hot diaphanous material. I think anybody that has studied black holes, I don't know if the person online has this picture in their head, but many of us have this image when we say accretion disk. We think of material flowing in, and kind of as it flows in, it heats up, it emits photons, and it kind of flattens out into something that's sort of a flattened structure, so that if you were to look at it face on, it might look like a frisbee. From the side, it looks thin. That's like the accretion disk. It's sort of this flattened structure that's accreting onto the black hole. In both Sagittarius A star and M87, the gas actually doesn't cool very successfully, and so it doesn't ever flatten down into a disk. So it's actually more like a big puffy disaster. It's an accretion flow. Mass still falls onto the black hole. But as I was showing you in that simulation with the stellar winds, it's not obvious that the gas is coming in from some preferential direction. There's like this puffy, hot material all around. And it does manage to fall down onto the black hole, but not in a tidy, orderly accretion disk way. This has a technical term. It's called a radiatively inefficient accretion flow. To put that in normal language, it means it doesn't radiate very well. It can't give up its energy, which means it can't flatten down into an accretion disk. So it just stays puffed up because it's kind of banging around with all this excess energy that it can't radiate away. I don't know if that satisfies our online person, but they can follow up. Okay, we'll come in front.
when you're coordinating all of the telescopes on Earth, how accurate do we need to know like the time of things and their location? Do you need to know it like within one wavelength?
So the time of things is really important. So yes, you must know it within one wavelength. And so long wavelengths give you a little bit more flexibility. They have literally a longer wavelength. So measuring those wavefronts is a little bit easier, but we have incredibly precise clocks at all of these sites in order to do that wavefront sensing, in order to do that clocking. And in fact, a major challenge of going to space is that you have to have an even more precise clock if you're going to receive the photons and then know that you're correlating it correctly against a site on the ground. And that's partly because how do you know where the spacecraft is in space? You send a light beam, you measure the time it takes, there's all these different time delays that you have to get right to know that your wavefront sensing is working. And so this is actually a major challenge. How precise is your clock? And we have really spectacular atomic and other kinds of really precise clocks in order to do the correlation so that you know exactly when your wavefronts are coming in and then you can correlate them in a computer later.
It's the same with the location of the site as well. You have to know the exact location.
Yes, although it's slightly less, you need slightly less precision in those locations than you do in the timing. The timing is really the most important piece of doing the correlation in the interferometric stuff. And you'll notice also the arrays are different in there, or the telescopes are different. Some of them are actually arrays of small telescopes that are talking to each other. Others of them are single monolithic beams. And so once again, you end up having different distances that you're talking about to get the right sort of measurement or sensitivity to the wavelength of light and the particular target that you're interested in. So yeah, but yes, all of these things matter. What's a jet? Great question. So jets, we think, I'm going to wax guessy for you as a scientist. We see jets in space. We know they're there. What we think jets are is a collimated magnetic structure. What creates that magnetic structure is not completely clear, but probably twisted magnetic fields. And then when you have particles in space that rotate around magnetic fields, because they're accelerating in a circle, they emit a particular kind of radiation that we call synchrotron radiation. And so a jet is a magnetic structure that is illuminated by particles zipping around the magnetic fields and emitting light as they do that. And the jet itself is probably just the magnetic structure, but we wouldn't see it if it weren't for the material interacting with the magnetic field. The magnetic field could just sit there and not show us anything if it felt like it. But if there's any kind of mass or, electrons to orbit around the magnetic fields, then it emits radiation and we're able to detect it.
So M87 and the Sagittarius pictures, but the M87, you could see the black circle in the middle a lot better. Is that because it's bigger or because of the time-lapse thing? Or what makes it so much more round and dark there?
It's brighter. It has, so M87, I took out this little chart. I had a chart. So Sagittarius A star is particularly troublesome, not only because it varies, but because all that tenuous, I keep describing this gas, it's just a very disorganized system. So there's lots of fluffy stuff all around, and it's not accreting in a nice, clean, and behaved way. M87 also has this puffy hot accretion flow, but its reservoir, we'd call it, of material flowing in is much more massive, substantial, and sustained. And that means that its accretion flow, even though it's hot and puffy, is just overall more stable and brighter. And that gives us you can just imagine trying to take a picture of something, that just isn't emitting very much light. It's going to be a little fuzzier versus something that's emitting a lot of light. It's much easier to get a cleaner, crisper image. So with M87, we're seeing, just a brighter structure that we can get that kind of whole image a little bit more clearly. The other thing that's a little bit uncertain about Sagittarius A star is if we don't exactly know the sense in which the black hole's rotating and exactly how that spin axis is aligned with our line of sight, whether it's rotating like this or rotating like this, the black hole might change a little bit the way the accretion image looks, the way the kind of light looks to us. So that could affect it too, but mostly it's just that M87 is brighter. Yes, we'll go 1, 2, 3. We'll do a little triangle right there.
When you were showing these pictures, we could see one of the rotating jets going. What sort of normalized for understand there are two jets, both sides, or do we see the other jet going the other way, or just because of the orientation, it's not bright enough?
Yeah, so a jet going along your line of sight is going to be Doppler boosted, which means we see the light more, it's brighter because it's getting kind of an extra Doppler boost. The one going away from you is Doppler deboosted. So any line of sight that's away from your observing is going to look fainter. The jet will always look fainter. We think jets are always jet and counterjet, but we don't know that for sure. We do see some systems where we've looked really deep and really hard and we can't find the counterjet. But you could imagine if the jet has to punch into a lot of dense material, there might be certain environments where it can punch through more easily, and then the opposite side of the system, the same might not be true. It might get absorbed by, some ball of dust and gas that's kind of in the way. So there's a lot of reasons you could imagine the jets not being perfectly symmetric, either in brightness or in geometry. Also, they have to interact with all this medium. So we do see jets that have sort of a clean structure in one direction and then a bend, for example, in the other direction, like they slammed into something and had to kind of redirect a little bit. And so you can tell they're not perfectly symmetric, but there are often a jet and a counterjet. There's no reason to prefer one direction over another, basically. Yeah. Oh, sorry. I'll go through. If you were a scientist, you'd say, I have a question and a comment. That's usually what they are.
Black holes found as galactic nuclei. Is that the exclusive place that you find supermassive black holes? And for part 2, if they are found in galaxies, do certain types of galaxies have more of a frequency of these supermassive black holes, like the types and shapes of them?
Yeah, that's a fantastic question. So as far as we know, supermassive black holes always are in a galaxy. There's a lot of reason to suspect we would not successfully observe a black hole if it wasn't in a galaxy. So I would say there is a strong detection bias against a wandering naked black hole. There's nothing that's going to indicate to you that the black hole's there. So you would have it could still interact with things, but space is extremely empty. So it would be hard for it to interact with things. So a future experiment that might get you a better answer to that question is called LISA. It's a gravitational wave detector in space that will actually detect the ripples in space-time from two massive black holes in orbit around one another. They basically are like egg beaters and they kind of whip up space-time and create gravitational waves. So potentially, if supermassive black holes exist in binary systems with no galaxies, you could still detect them gravitationally. But we don't have that experiment yet, and we don't have a constraint on that particular question yet. Almost all, I would say all of the supermassive black holes we've ever detected have had a host galaxy around them, as far as we can tell. Some of the very bright ones in the distant universe, the galaxy is very faint and hard for us to see. And usually they have jets kind of pointed along our line of sight that kind of blind us from seeing the rest of the galaxy. So we don't know for sure that they're in a galaxy, but we think that they are. So I would say, I don't know what, scientists, 95% confident black holes live in galaxies. As far as which types of galaxies, we see more massive black holes in more massive galaxies, not a super profound statement. But as we move down the galaxy chain from massive galaxies to lower and lower mass galaxies, we become uncertain. So down at the very lowest mass galaxies, we don't know whether they have black holes in them or not, partly because it's difficult to make that measurement, and partly because when you get down to the low mass galaxies, the galaxies themselves become very disordered. They don't look like pretty spirals or elliptical galaxies. They're kind of more these bumpy, clumpy, not very galaxy looking galaxies. And in those systems, it's difficult to search for black holes. Yeah, sure. Please.
You have an explanation for that? Massive, these black holes, so early in the universe.
Yeah, so we have a lot of evidence, and in fact, we have a huge mystery, a conundrum. So graduate students, undergraduates in the audience who want to think about black holes, this is a new one. So we see lots of black holes in the early universe. I think Thomas is in the audience. Thomas will help me know, isn't the current like photometric one like redshift of 14 or something? That was the one that we're going to talk about in a journal club this week. So these are really high redshift objects. They're in the very, very, very early universe. So we see black holes, what we think are black holes, very, very energetic systems that are probably accretion driven at extremely early times, very, very early in the universe. But perhaps the bigger mystery is not whether or not we see black holes in the early universe, but one of the things the James Webb Space Telescope has showed us is an incredibly large number of black holes at more intermediate redshifts. So things not quite like the super record holders closer in, but James Webb went out and looked at the sky and found hundreds and hundreds more black holes than we thought could be there. These have a very cute name. They're called little red dots because they look like little red dots in the image. And they probably are sort of a black hole that has a lot of dust around it, and that causes the light to be absorbed and re-radiated, which is what makes it look red. And there are way too many of them. Like way too many of them by like an order of magnitude or more. And so this is something that if you go look in the literature, look up little red dots, you'll be like, oh my God, there are like hundreds and hundreds of papers just in the last 2 years trying to figure out what is happening. This is not a thing we expected. So lots of black holes in the early universe. Yeah.
So, compared to these two black holes, what angular size do you expect for like the next candidates down the list? And then also, it's so hard to tell with mass. How did you target M87 in the first place? That would be angularly large enough to see.
We had a pretty good guess about the mass from other very indirect measurements. So we had a sense for what the mass should be. And we had one, for example, we had gas dynamics. So if you look out at larger scales, you can see material rotating around M87, and you can kind of infer a little bit like we do with stellar orbits, how massive the black hole would need to be guiding the orbits of this gas at larger radii. So we had that, and then we had some dynamical measurements also for M87, but the two of those measurements, a dynamical measurement and a gas measurement, actually disagreed by a large fraction. And so then when we collected the image of M87, we actually found that we agreed pretty strongly with the gas dynamical measurement. And so we found concordance between two of the three measurements, and we kind of threw out the third one. So we had a pretty good guess as to what M87's mass was, but nothing like the precision that we can get from doing the horizon scale imaging, and nothing like the precision we can get from Sagittarius A star with these stellar orbits where you have like many stars and you can do that measurement kind of with more than one test particle. But let me see if I can answer your other question in my slide deck here. I think I have one. Yeah. Okay, so this is a shout out to my grad student, Nicole. So this is the so-called ether sample. So these are a couple of sources here that we have imaged. This is a picture of the ring diameter or plot here. This is a little more technical than most of the talk. This is the ring diameter. You can see Sagittarius A star and M87 are over here. They have very large ring diameters of like 50 micro arc seconds. And the other next best targets are in here. So they're more like 10 micro arc seconds or less, a few micro arc seconds, and we can't quite get there yet. But you can see it's not zero, right? They're fainter. That makes them harder sources. This is a brightness. So they're fainter sources. not great for doing imaging. And they're much, harder, they're much smaller horizons, much smaller projected image scales. But maybe with next generation observatories, if we can get more observatories into our arrays, get better resolution by going to space, we might be able to get after some of these sources in here. But you can really see these two sources stand out, right? They're different than the others. That's the reason we can image them right now. Yeah.
Question, but do we call all black holes supermassive black holes?
No, that's not a simple question. Yeah. Well, we have, we have imperfect naming. So there are two kinds of black holes, is the way the story goes. One class is called stellar mass black holes, and one class is called supermassive black holes. Stellar mass black holes come from explosions of stars. They leave behind black holes that have masses of tens, maybe hundreds of times the mass of our sun, right? You had to have a star that exploded that made the black hole, which means they have to have masses that are sort of similar to the masses of stars. Stars can have masses, up to maybe a few hundred of times the mass of our own sun and down to very small masses, but those ones don't explode. So usually you get a black hole that's got something like 10 to maybe 100 times the mass of our sun. And then you look in the centers of galaxies, like the question about galaxies and whether they host black holes. And when you look in the centers of galaxies, the black holes all have millions to billions of times the mass of our sun. There's a big gap between 100 and 1,000,000. And so we call the little ones stellar mass black holes. We call the big ones supermassive black holes. And you might ask yourself, what's in between? And we cleverly call those intermediate mass black holes. No joke. We really call them that. And we can't find them. So it's confusing to astronomers why that is. It could be, I've given you kind of a clean explanation of how you get stellar mass black holes. Stars explode, they leave behind black holes. We can explain the physics of that. It would be a long explanation, but we can do that. Supermassive black holes, we're slightly less confident about how they actually start and become so massive, but more or less you start with something kind of massive and you just throw a lot of gas into it, like as fast as you can, as early in the universe as you can, and you get something massive. It's a little more complicated than that, but something like that. And that tends to happen in the centers of galaxies because the galaxies funnel all that gas into the middle. And so then you can just build up that black hole mass really fast. The intermediate mass black holes, for sure, we thought we'd find them. I mean, why would you have a gap between, a few hundred and 1,000,000? There's just not a good reason. Why not have 10, 1,000 or something? Like, there's just not a good explanation for why you'd have this big gap unless those two formation scenarios are just really totally distinct from each other. But we have looked and looked and looked and looked, and it's really, really hard. We have like a handful. So you've got like hundreds of thousands of one, probably hundreds of thousands of the other, and like a few in the middle. So this is an ongoing confusion and source of research. And I mentioned the LISA space-based gravitational wave detector. One of the things it's going to be very sensitive to is actually an intermediate mass black hole in orbit around a supermassive black hole, which sounds a little crazy, but it's not that crazy. If, massive stuff kind of congregates in the centers of galaxies, you could imagine an intermediate mass black hole spiraling around a massive one and giving a very distinctive gravitational wave signature. We call those extreme mass ratio in spirals. We really love acronyms, so you can just call them EMRIs if you want. But that might be successful at helping us find more of them. But really, it's a pretty pernicious question why the universe doesn't make them or why we can't find them. And it's not really clear which two of those things is happening. Not really. They sort of look like, I was saying that when you get down to that low mass end of galaxies, the galaxies are kind of a bit of a train wreck. Like, they don't really look like normal galaxies. They're kind of patchy and sad, and they have little bright spots over here, but not really like a kind of structure. We sometimes find intermediate mass black holes in these kind of ragtag little baby galaxies. But every time somebody detects one, then somebody else comes and says, no, it's not that, it's something else. It's like and the debates go on forever about whether this one is really an intermediate mass black hole or not. And then coming from the gravitational wave side, the LIGO Virgo Cagra gravitational wave observatories have started to find more and more massive stellar mass black holes. So, you know, maybe we could march from like 100 to like 500. We're not quite sure, but certainly the gravitational wave observatories are pushing our limits a little bit. We're finding gravitationally stellar mass black holes that are a little more massive than we thought. So maybe if you can build, you know, either by stellar explosions or by merging together 100 solar mass black holes, you could build something that's like 500 or 600, maybe 1,000, and then you could throw gas onto it, and then you could make an intermediate mass black hole, but it might require a combination of mechanisms to really kind of get that. And it might kind of confuse that origin story about where they come from if there's a lot of different things going on.
With all the data simulation, we know or have an idea if what came first, black hole or galaxy?
That's a super good question. And no, as far as we can tell, with the data we have and the knowledge we have from our theories, or the knowledge we built with our theories, they look like they basically originate together and they evolve together. So as soon as we can detect stars in structures, which might be the kind of earliest types of galaxies, we've already got supermassive black holes, which is not really what we expected. And so this is part of this thing about little red dots I was mentioning. Every time we go out and we look, the black holes are big and they're there really fast. They're there way sooner than we would expect if they needed some kind of, you know, precession of formation, like galaxy forms and then later black hole forms. We would expect to see fewer of them at early times, and we just don't. They're always there. So it looks like the black holes and the galaxies co-evolve from very early times. And that actually requires that you evoke some pretty weird theories to build the black holes massive enough early enough, including this currently in vogue theory called direct collapse, where like a bunch of mass just kind of gets together and then goes boom into a black hole. Like, no joke. That's kind of the state of the art right now. So I mean, it's really hard. You need some very specific conditions to get it to do that, but the theories are out there. And if you have very pristine, very early universe gas, you might be able to make that theory work, where it just collapses really fast, really early. Can you yell a little louder? I think either could be biased. And I mean, the bias coming from the scientists is already imprinted on the experiment, just to be clear, right? I don't actually know how differently that was treated. I could go and ask some of the people that actually were kind of managing the data. I think when we were asked to classify, into a couple of groupings that already sort of set an expectation of whether or not it was going to be more in this class or in that class. And those expectations may have actually already come from the subclasses that were in the AI training. So I'm not really sure how to answer your question because I don't know exactly what our machine learning experts did with the human and, you know, classified data versus the AI classified data, whether they handled them differently. I think the human classification was to help build trust that the AI wasn't doing something wacky. So to some extent, I think there was already confidence on our side that the AI was doing a good job of classification, but we wanted to build our confidence that that's true, sort of make it a little more explainable to us. I don't know if that answers your question, but we could talk more. Yeah. I'm going to stay all the way in the back and then we can come forward. Yeah, no, we definitely do not wait to be on the other side of the solar system. That would be an even bigger interferometer than we currently envision, and make telecommunications very hard. So all of the observations I was showing are all done in the course of about a 6 or 7 hour time frame. And so the different baselines that we were tracing out have to do just with the globe rotating, not with our entire orbit around the sun. That would be awesome, but hard. And so these are all over the course of about, I think our longest traces are typically like 4 or 5 hours on a particular object. I'm not sure I'm answering your question exactly though, but those baselines are taken, those different ones are collected over the course of just one evening. It is. It is. It's just harder, right? To get a longer baseline, you have to figure out a way of beating the globe, right? Right now, we've got telescopes that are basically, some of them are almost fully the diameter of the Earth apart. And so to get a longer baseline than that, you have to figure out a way to get off the Earth. And that the best way we can think of right now is to put something in orbit around the Earth, because then you can get, 2 Earth diameters or 4 Earth diameters or whatever, as long as your telemetry is good enough to communicate back and forth. So that's the best hope we have right now for getting a longer baseline. There's other things you can do, patching in more observatories on the globe, which improve your sensitivity and kind of help you fill in other parts of the image, but they don't get you more precise resolution. Yes. Yeah. That's exactly right. And so we've lied to you a little bit. We actually have a third night. So we only published 2017 and in 2017, April 2017, we observed Sagittarius A star for 3 different days or nights, however you want to think about it. We can observe during the day because it's submillimeter, so it doesn't, but 3 different dates. And we've only published and showed you the image from the first 2. And the reason we didn't include the third one is that we were observing Sagittarius A star simultaneously with an X-ray observatory called Chandra, and an X-ray flare went off during that time. So we know at least at another wavelength that we think is also tracing out emission near the event horizon, there was some very spectacular variability. And we eliminated that from our analysis because that makes the imaging really hard. If we know it's varying, we know we can't trust our synthetic imaging, our aperture synthesis. So we just left it out. And there is a very active project that hopefully will have results in the next few months, analyzing that third night. So trying to take the baseline that we have from the first 2 nights, where when we look at the source with all sorts of different observatories, it looked like it was pretty quiet, like it wasn't doing anything fancy. We used that to make our baseline image, and now we can compare that third night of data against that baseline image and look for signatures at the horizon scale that might trace out that same variability. So it's very cool stuff, but it is extremely hard to take an image when you know your source is doing something wacky at the same time. Yeah, it's a good question.
We'll take one more question. So. Is it possible to accurately measure the weight of rotation of the black hole? And if so, how do you do it?
Yeah, so the way we do it is by comparing. So the question is, how do you measure black hole spin? So black hole spin is very hard to measure. There's a lot of different ways at it, but the 2 levers we have with this are whether the spin of the black hole is sort of is rotating one way versus the other way with respect to our line of sight. That can change actually how the shape and size of the image a little bit. And so the way we can try to make that measurement is by simulating black hole images with different spins and then comparing those simulations to our image and saying our image is most consistent with a spin that looks like this one or this one, and less consistent with a spin that looks like that one. So for example, a very, very low spin black hole might have a very characteristic kind of signature, and a very high spin black hole would have a different characteristic signature, and you're just comparing your image against those simulations to see which one is more consistent. That's one way of doing it. The other thing that people are really excited about right now is trying to use those polarization signatures, those magnetic field tracers, to try to use that to help you get a sense of the magnitude and the tightness of the twisting of the magnetic field. And that is another way of trying to back out the spin. So when a black hole is spinning, we think it does this thing called frame dragging, which actually drags the fabric of space-time with it while it rotates. And that's the thing that changes some of the sort of size and, the sort of the signatures that show up in the black hole image. So we use general relativity as our way of trying to constrain that. And then if you find something that's really weird or wacky, you might then be able to challenge general relativity. But right now we're just using general relativity and not challenging it in that particular measurement.
Great. We have one last question from the
Sure.
audience. So does the rotation of the Earth help collecting data, or does it obstruct it?
Yeah, so the rotation of the Earth is both good and bad in this case. So we need all those different baselines, the long ones, the short ones, the ones that have orientation, north to south or east to west. Those give us different views of the source. And when we put them together, that gives us the full image. And so we kind of need all those different relationships between the different telescopes. And we only get that variety because the Earth rotates. And so different combinations of telescopes can see the target we're looking at the sky at different times over the course of the night. So if the Earth didn't rotate, we'd just have one view of Sagittarius A star. We wouldn't have all the different possible views of Sagittarius A star. So it helps us build up a more robust image. On the other hand, because the Earth is rotating, we don't always have our most sensitive telescopes looking at the black hole, for example. So your sensitivity varies over the course of the night, and those variations in sensitivity are one of the things that complicates studying variability. It's hard to know if something is changing if actually your instrument is becoming more and less sensitive. And so it's both helping and hindering you at the same time.
So thanks a lot for this amazing presentation. Please let's thank everyone. So before you all leave, I just wanted to introduce the next public talk, which will happen on February 18th, and it will be given by postdoc Lauren Rhodes.
Who's awesome. Oh, there she is. Who's here and awesome.
Doctoral research fellow here at McGill University. Her talk will be 50 years of gamma ray bursts, the most powerful explosions in the universe. Please join over for this talk. I want to thank you for being so engaging, and it's really lovely to see this.
For oohing and awing. So behaved.
Before you leave, another thing. So for those who scan the QR code, I have the name of the winner, who is Danica. So if you're Danica, please grab one of the TSI. And yeah, thanks everyone, and we'll see you at the next talk.